I would like to thank the organizers for inviting me for a presentation regarding big data and data analytics. My presentation will be actually composed of several parts. First of all, I would like to show what are the practical motivations for the big data and how the big data are influencing statistical science these days and data science. What kind of practical examples we have, this would be the second part of my talk. And then the third part would be actually related to the question of design. If we are using statistics, machine learning, or artificial intelligence for the inference problem, for making decisions, for example, like properly functioning or not properly functioning, a good or bad situation in financial markets, healthy or sick regarding the patient, then it is a very good idea to limit ourselves to those features and these segments of data sets that are crucial, that are critical for the decision on hand. That's why we are talking about the design problem. And as the fourth, maybe the most technical part of my talk, I am going to just give you a very, very short account on what's going on these days in statistical science and how what is known as functional data analysis is responding to the current needs of the big data community. So without any further delay, let us start the presentation. And let's start with the good and bad message. These days, we really have enormous capabilities in data collection. As an example, I can talk about a bridge built recently in Shanghai, China, that has 20,000 different sensors. Each sensor is producing about 2,000 data points per second. The data are collected in real time. And then, based on those 20,000 sensors, each churning out the data 2,000 points per second, we need to make a decision regarding the properly or not properly functioning the bridge. In my presentation, we are also going to have a look at the alternative energy generations and medical diagnostics and finance. So the good message is, yes, we can now collect, store, and process enormous amount of data. Well, this doesn't necessarily mean, however, and that's the bad message part of what I'm going to tell you. The fact that we are collecting lots of data doesn't necessarily mean that we are better off in terms of the quality of the decision we are making. I have just witnessed a very short presentation regarding the optimal detection based on the computer vision. And for example, if you have a hexagonal stop sign, the white stop letters written on the red background, and if you just put a small yellow post-it tag, the automatic recognition system will not read it as a stop, but as a 35 miles per hour sign. Well, this is a very big difference. So we really have to be very careful in how we analyze the data. We cannot just blindly apply artificial intelligence, statistical, or machine learning tools. But like it or not, the big data are everywhere with us. They are in business, in government, and in industry. Może po prostu wytrzymał. No, to jest pewne. So we like it or not, we have the big data everywhere in business, in government, in industry, in health sciences. So let's move on to the first example. Our first example, essentially what is being shown on the presentation file, are the wind turbines. Wind turbines, well, many countries these days are relying on the aeolic energy, and the wind turbines are providing for a good percentage of the alternative energy generated. And wind turbines are mounted on the high masts, so they are notoriously difficult to observe. What people do is actually they mount sensors in turbines within the turbine set of the wind turbine, and then using the remote observation system, like for example a cell phone or any other signal transmission system, we can make a decision regarding the quality of the wind turbine. Is it working properly, or does it need to be replaced? And that's a very important part of the monitoring of the properly working wind turbine. The data are really big. You can just compare on this picture the size of a human to the size of the wind turbine. So we are really talking about the massive objects generating massive data. Let me be a little bit more technical regarding this data. Usually the turbine, when it is monitored by the automated system, the monitoring signal is the acceleration signal, properly filtered. And such acceleration signal is observed with the frequency 2 kilohertz. That means there is 2,000 points, observational points per second. So if you have several turbines, if you monitor them with the 2,000 data points per second, you really produce massive data sets. Another problem related to energy. Maybe most of the conference participants should know that 95% of Polish energy is generated by burning coal, and as much as the black coal is now significantly reduced, we still have in front of us 300 years of relatively problem-free digging in the open pit brown coal. So this picture represents the machine that actually takes the ground from the above, and then it's digging into the brown coal layers, and then from this huge machine the conveyor belts are transporting the brown coal to the energy plant. The coal is burned, and that's how we produce energy. Well, if you look carefully at this problem, at this picture, the problem where it is generated is actually in the gearbox, which is now denoted by the yellow circle. This yellow circle and the gearbox, which is pointing out, is where the crucial problem of this machine is located. There are also sensors attached. Again, as before, we are monitoring the acceleration signal with more or less the same speed as with the wind turbine, which is 2 kilohertz, 2,000 data points per second. Now here, the problem is much more serious. That is, any stoppage of this machine, if this machine stops working for a day, which means if the wheel bearing, which is in the center of this machine, is not properly working, the stoppage of this machine is about $5 million per day. So it is a very expensive tool, and we better have a very good monitoring system to avoid costly stoppages. Let me move on to the next example from a totally different part of the world. Well, this actually is a econometric time series which is describing the price of energy. We have the Scandinavian energy market, and the prices here are shown in the Norwegian crowns, the NOKs, per megawatt hour. And we have observations in every 5-second intervals continuously throughout the day, and we have those observations available here. You observe this type of data, and since the energy is now entering the regular market, there is a concept of the spot price of the energy, which depends on the time of the day of the week of the month, and the month of the year, because we have a seasonal fluctuation of the energy price data. You would like also to be able to process such massive data sets, and you need, well, advanced statistical procedures for that. Let me move on to the next part of my presentation, which is the actually electrocardiogram. I think most of you participants of this conference, at least once in your lifetime, you had the electrocardiogram signal monitored on you. And there are essentially 5 important elements of the electrocardiogram. The so-called curves, and they are denoted by P, Q, R, S, and T. Depending on the shape of those curves, practical side of the medical diagnostics is to see what is the shape of those P, Q, R, S, T curves and whether they correspond to the healthy pattern or the sick pattern. Next example comes from the car business. Here on the picture, what we are seeing are cycles of the engine. And when you enter the car, you can actually listen to your car engine, idling the car, which means putting your gear on the neutral, starting your car and listening to the motor. The signal here represented is the actually detrended acceleration signal, so it's a little bit like listening to a car. Anyone driving a car knows that if the engine has hiccups, that is, if the engine is not working smoothly and uniformly throughout the time unit, then there is a very good chance this engine is not working properly. So again, the similar story returns. We have the signal is observed, it can be processed, there is lots of data brought by the signal, and we want to make a decision regarding the, for example, engine. Is it working properly or not? We are processing lots of data. For example, if you collect the data with the 20 kilohertz frequency, which means 20,000 data points, you have already millions of data points in just minutes of the signal. And the challenge these days, the challenge when we talk about the data science, the challenge when we talk about the machine learning, artificial intelligence, and statistics, is to make inference. That is, make a decision. Properly working, not properly working. Healthy, sick. So let's try to be a little bit more technical, and let's try to explain you guys how in the reality of the signal analysis the decision is made. The modern computational tools that actually are very useful in massive data processing, for example, for the acceleration signals generated by a vibrating machine, are based on so-called spectrogram. What you see on this picture are just a bunch of stripes, the vertical stripes. You may be surprised of the maybe not high informational content of this picture, but if I'm going to tell you that the deep blue color corresponds to, let's say, small values, and the closer you get to the yellow color, then the values are higher, then this is already informative. Now, this picture is so-called time frequency representation for a signal. If you have a massive data, what you do is you introduce a sliding window on your signal. You calculate a fast Fourier transform on each of the sliding windows. You slide the window, so then you have a family of Fourier transforms. Those are those vertical stripes. Sometimes those vertical stripes are of the brighter color. Sometimes those vertical stripes are of the darker color. The darker color corresponds to the lower values. The brighter colors corresponds to higher values. And so, essentially speaking, we have the shape, or even better, a frequency signature of the signal. So on the left-hand side of this picture, on the vertical scale, there are the frequencies, and you can see that in a specific frequency band, we have higher values for the spectral densities, and in other frequency bands, you have lower values. So that would be like a frequency signature for a signal. How the story goes with the electrocardiogram. Let's consider two regular patterns with the electrocardiogram. Let's consider the NSR, which is the normal sinus rhythm, and this is denoted, illuminated on this picture by the green color, versus the premature ventricular contraction, which is in the gray color. You see those two curves are completely different when we see them. Now, is there any way that a machine analyzing signals will be able to tell whether a given signal from the patient is closer to the green curve or is it closer to the gray curve? In order to do that, we need to be able to describe massive data, which are behind curves, because if you have a high-frequency data collection, each curve may correspond to thousands of data points. And now when you introduce the description of the curve, it is like introducing of the features. Anyone who did at least once in his or her lifetime Fourier analysis, this person knows that the essential feature of the Fourier representation of a function is a frequency. So essentially, when we talk feature, we can talk a frequency. But not only, we can also use other representations and define features within those other representations. And, well, visualizations are based on segments of the data, and we would like to let all the data speak for themselves. Well, guys, this is it. Now I have to move on to the technical part of my talk, because we need tools to make decisions. And those tools are based on quite advanced statistics and math. So when we are talking about big data, let's think about curves. Now, if you have 20 kilohertz, that is 20,000 data points per second, you can think of a 1 second as a segment of a curve. So now a curve will represent 20,000 data points, and it will be just considered a single object. If you observe with the 2000 per second frequency, which is 2 kilohertz, then you will have one curve representing 2000 data points. So a very convenient way of representing big data is what we call in statistics a functional data analysis, which is nothing but a space of curves. The most popular space of curves in which we can introduce different metrics, different concepts of the distance between the curves, and then features of those curves, is the Hilbert space. So those of you guys who would be interested in following up on the development of the big data in statistics, you guys better learn what is the Hilbert space, because this would be like a starting point for the high-dimensional data analysis. For example, let's think about the electrocardiogram signal. We have 5 features, P, Q, R, S, and T. We can find such a, as we will call it in statistics, a representation or a base in the Hilbert space, then those 5 features will be exactly represented, and then you can reconstruct the function from those features. Okay? Okay, so now if you already agreed that the space of your data, of the high-dimensional data, is the Hilbert space, let's review the classical tools that are available in this space for the data analysis. The tool number 1, of course, is the expectation. Now, what is the meaning of the expectation? When we have sequence of data points, we would like to know what is the most typical place where this data are around. For example, if you have thousands of electrocardiograms, well, if you ever took electrocardiogram, then you are lying on the bed for several minutes, and of course, several hundreds of replicates of electrocardiograms, each replicate, which is about a few seconds, are collected, and then sort of a pattern of the work of your heart is collected. What would be the average pattern of a function? Well, that's exactly the concept of expectation. So what will be your typical pattern using the functions? And for this concept, we are actually utilizing the scalar product in the Hilbert space, and we have that the expected value is equal to the actual point-wise expectation calculated for every point, which means if you have several curves, each collected with, for example, 20 kilohertz frequency, at each of those 20,000 points you can calculate the simple numerical average, screen those hundreds of signals at those 20,000 data points, and you will get a curve which will be considered a mean curve. A mean curve would have the meaning of the typical location of the data. When we are talking about the location of the data, we need to talk about the spread of the data. Spread is the energy. Spread is the amount of variability in the data. How to measure a spread for high-dimensional data, how to measure spread for functions. And well, we have tools, again, based on the Hilbert space. We have, well, some integration inequalities. I don't want to bore you to death with all the technical details. Just let me tell you that the name we associate with this measure of spread for functions is the operator of the covariance. Maybe to those of you who ever did any statistical analysis, the concept of correlation covariance is already known. And yes, what covariance is doing is assigning a number to the numerical observations. So in the Hilbert space setup, when we deal with the big data and you use curve to represent the big data, we are talking covariance operator. That means you take set of curves and you calculate covariance, which in return gives you a curve. So covariance would be considered a curve. I need to torture you a little bit more with the math theory, because now, of course, anyone working with the big data would like to solve the fundamental question. How to reduce dimensionality? Do I really need to work with 20,000 observations per second each time I see a wind turbine, each time I work with the electrocardiogram, each time I work with the financial data describing the energy markets? And the answer is, of course not. In most of the instances, instead of working with very high-dimensional data, you are working with so-called principal components, especially if what you are interested in is describing the variance. And the principal component method is also available for the big data, and this is the definition. Okay? So, as I said, if the above math is looking like a rocket science, well, it is somehow involved, but I just would like to spread the message that it is worth to learn math these days in the context of the big data. Let us do a little bit of a summary, which I would call the Functional Data Analysis 101, which is sort of a basic class on the high-dimensional data analysis. Assumption number one. We look at high-dimensional data as functions, so we are not scared anymore because we have tools to work with the functional spaces. Millions of data points are integrated into one object. So instead of talking, let's say, 50, 100, 150,000 data points, you are talking about one function. Then, so your collection of data is now reduced to collecting functions, and the sophisticated math based on the principal component analysis is reducing those curves into few real numbers. Numbers, I repeat. So you start with, let's say, 20,000 dimensional vectors, you put them together into curves, you do the principal component analysis on those vectors, and you end up with just few numbers that will describe, for example, 80 or 90% of variability. This is really something very, very useful. Okay? Let's have a look how this works on the electrocardiogram. So again, think about it. Think about the way that the automated diagnostic system would be designed based on those curves. Because of course, when we just look at those curves, it is obvious that the green curve is very different from the gray one. But what if you don't have time? What if you would like to produce an automated diagnostic system that will detect special features of those curves? How to do it? Well, you have another picture of the NSR versus premature ventricular contraction. And on this picture, the situation is well, much further from evident as it was in the picture before. But still, you see the differences between the gray and the green, but you would like to have the algorithmic approach. The algorithmic approach is based on the function which is available in the statistical software R, and this statistical software is called the FDA. So when you look carefully at the FDA eigenvalues, you will be getting different eigenvalues for different types of curves, which means you can do diagnostics. You can move on to the analysis, and then you can have the solution of your electrocardiogram analysis problem. That is, if we look at the left-hand side, which is representing the normal behavior of the heart, the first eigenvalue is of the order of 392, whereas on the right-hand side, the first eigenvalue is in the order of 1000. The difference is huge. So obviously we are dealing with two very different systems, and reduction of dimensionality is quite effectively presenting the problem. Now let's move on to the conveyor belt, the excavation machine, and so on and so forth. What's going on now here? Well, again, we have a signal generated. We look at this signal, and we are, instead of considering 20,000 per second signals, we just have 8 fundamental functions and 8 fundamental numbers. How those functions, the functional principal components, as they are called in mathematical statistics, how they are related to each other. If we analyze the next picture, the first 4 functions, those functions are aligned in the decreasing order of their influence into the final variance, are represented here. Those pictures on the diagonal show us the shape of the main functional components, and the cells beyond the diagonal are showing the correlations. Principal components should be independent, so the more chaotic look pictures that are beyond the diagonal, the better for us. And actually, those frames beyond the main diagonal look pretty much chaotic. So what we are doing here? Well, first of all, you want to do functional data analysis, you have to be able to switch between different computer environments. The starting point is formatting your data. You usually do it in various environments, in Python. Then if you can stream the data into the R, in R we have modules that help us analyze the functional data analysis. Then you can do the functional principal components. And essentially speaking, you have from the functional components the decision regarding the shape. Is it the shape corresponding to the healthy patient or unhealthy patient? Is it the shape corresponding to well-functioning machine or not well-functioning machine? And at the end of the day, you can also validate those systems because, well, one of the big advantages of statistics is our ability to validate our results. For example, let's say deep neural networks can give us a way of finding the most efficient collection of the principal components. But it will be a statistical science that will tell us whether these functional components are giving us a significant result, a proper result regarding the diagnostics. I think I will stop at this point. I have arrived to the end of my presentation. So thanks a lot. Should you have any questions, do not hesitate. Write me at my email, which is jleskow@pk.edu.pl.